This presentation is about image sizing and compression. It's all about the bits and bytes. For web pages, file size is extremely important. If pages take too long to load, people aren't going to stay on your site. Not only do we want fast-loading images, we also want them to retain a certain level of quality. For this, we'll need to understand how images work. Starting off, we'll discuss pixel count. How many pixels by how many pixels? Then, we need to cover palettes and color depth. With this, we'll know how many bytes the raw images are using, as well as the limitations. Common compression algorithms will also be covered. Some forms of compression work better than others, depending on the type of data. For images, the data can take on many forms. Popular image formats will also be explained. Here, we'll focus on GIF, JPEG, and PNG. Images are created with many little dots or squares. We call them pixels. The more pixels in an image, the more detail we can see. With several pixels grouped together, we start to see a visual representation of something much greater. These images represent 12 pixels across by 12 pixels down. 12 times 12 is 144 pixels for each image. It doesn't seem like very many, but these are tiny pictures. They get bigger. Old computers had a resolution of 640 by 480 pixels. That's 640 pixels times 480 pixels. That's 307,200 pixels. Seems like such a small picture, but that's a lot of pixels. Some cameras will save pictures as large as 5,000 pixels or more across. At 5,000 pixels by 3,000 pixels, a single image will have 15 million pixels. That's 15 million dots, and each one has a color. Color depth and pixels. Each pixel has a color, and the color component for most images will be in an RGB format, red, green, and blue. For a color palette, each of the three color components, or channels, has its own byte. However, the palette is limited to 256 different colors. Each pixel holds a 1 byte value that indexes a specific color in the palette. The palette is used as a lookup table for each pixel. Also referred to as 8-bit color, images with very few colors work best with a palette. Here's an 8-bit image. The palette turned out quite nicely, but it looks pixelated. Sometimes this is the look you want or need. An 8-bit image creates a small file, and they load fast. This image is 600 pixels by 333 pixels. That's 199,800 pixels. With an 8-bit palette, that's only 199,800 bytes of raw data. The palette will also add an extra 768 bytes. This is the same image in 24-bit color. Just like 8-bit color, each color component has its own byte. But there's no palette. Each pixel will store its own color. Instead of being limited to 256 individual colors, 24-bit images can utilize 16,777,216 different colors. At 8 bits to a byte, we multiply the width times the height times the bytes per pixel. The raw data of this picture now consumes 599,400 bytes. 32-bit images usually retain the three 8-bit color components, but the fourth component is the alpha channel. The alpha channel holds a value representing opacity. Here's some HTML code to animate an image that has an alpha channel. This code doesn't have an opacity value. The opacity will be managed entirely by the alpha channel in the image. Here's King Boo. You'll notice that the crown, eyes, mouth, and tongue are completely covering the background. Everything else is blending with the background. The alpha channel is used to blend the background with the image. An alpha channel will increase the raw image by an additional 25%. Since the alpha channel is often comprised of extremely uniform values, once compressed it takes up almost no additional space on the hard drive. For a quick review, pictures are made of pixels. Each pixel holds a palette index or actual color channel data. A palette has 8 bits per pixel and a maximum of 256 colors per image. 24-bit images use 3 times the data and can display 16,777,216 colors. 32-bit images use 4 times the data and allow for opacity. We know how to calculate the size of the raw data. All of this information is extremely important for compression. Compression algorithms can only do so much. The best way to reduce the image file size is to reduce the number of pixels. Shrink the image to the absolute minimum acceptable size. Compression algorithms alone will not save you. If your image only has a few colors, consider using a palette. Converting a 24-bit image into an 8-bit image will reduce the raw byte count by 2/3. The best compression rates depend on how you prepare the data. There are only a few compression algorithms in use for images: run length encoding, Lempel-Ziv algorithms, and Huffman coding. Run length encoding. This is one of the easiest to learn and implement. Start by counting the number of consecutive bytes, store the count followed by the byte value that it represents. This algorithm is only good for repeating data. Every time a new byte value is encountered, at least 2 bytes are written. It's quite possible to double the file size with this algorithm. JPEG files use run length encoding. It's exceptionally efficient for the red and blue chroma channels of an image. We'll cover that part in a bit. LZ algorithms. The LZ algorithms look for matching segments within a data stream. Unlike run length encoding, many different bytes can be encoded all at once. The length of the match is stored as well as the offset to the match. This algorithm works quite well for images because many similar pixels and patterns are often grouped together. For even better results, the RGB components are separated before compression. By separating the colors, there's a greater likelihood of locating a repeating sequence of values. LZW is used by GIFs and PNGs. Huffman coding. Unique about Huffman coding is the fact that it doesn't rely on a fixed byte length. It's a variable bit length algorithm. Depending on the frequency of certain characters, a binary tree is formed. Starting at the first node, each bit in a consecutive sequence determines which branch to traverse. A 0 will go in one direction, and a 1 will go in the other. The scan ends when a leaf is reached. The leaf represents a byte value for the uncompressed data. In this example, letter A is reached from branch 0. If we follow branch 101, we find B. 101 leads to C, 110 is D, and 111 leads to E. In a fully formed tree, some paths will require more than 8 bits to reach an 8-bit character. Because of this, a purely random dataset is almost impossible to compress. For this to work, we require several bytes to have a high frequency of occurrence within the dataset. This algorithm is used by JPEG and PNG files. These are all lossless compression algorithms. By understanding how pixels are stored and the associated compression techniques, we can select the best file format to conserve space. GIF files, they lose data from reduction of color depth. They're limited to 256 colors, and they use palettes. With LZW compression, they work best with solid colors. PNG files, there's no data loss, supports 24-bit images for 16,777,216 colors, and they support an alpha channel for an opacity layer. It uses 2 types of compression, LZ77 and Huffman coding. Combined, it's called the deflate algorithm. Even with compression, the files can sometimes be very large. This format is best used to preserve the original data. JPEG files. Data is lost. JPEGs lose a lot of data. They support 24-bit color. They also use run length encoding for half of the data. The other half is used with Huffman coding. JPEGs offer extremely high compression rates, and small images will show distortions. So, why do JPEG files lose data? The compression algorithms don't lose anything. It's lost while the image data is being prepared for compression. Random, unorganized data is almost impossible to compress. JPEGs do their best to organize that data. The JPEG file format is extremely unique. It was created by an electrical engineer. Instead of processing the data in a digital way, the data is processed as though it were traveling through a series of analog circuits. To save time, we'll just skim over the basics. The red, green, and blue channels are first split into luminance and 2 chroma layers. We lose data in this step. The values are approximations. Each layer is broken into 8 by 8 pixel grids before going into a discrete cosine transform and a quantization process. Once again, we lose more data. With small images, this is the step that introduces noticeable distortion. Then, the data is organized in a zigzag pattern and normalized through a DC-AC separation. Yes, that relates to direct current and alternating current. Just a bit more to go. The differential pulse code modulation step is a predictive comparator. More data loss. Quite the miracle we still have an image at this point. Finally, the data has been filtered and organized in such a way that the compression algorithms are extremely efficient. Okay, let's go back to King Boo. For the background image, we've set it to 100% view width and 100% view height, with the VW and VH units. A good way to find the needed picture size is to take a screenshot and measure it out. I'll just copy the screen with the print screen key. Then I'll paste the image and crop the area. Then we'll check the image information. It shows 1680 pixels by 949 pixels. Let's resize the original image to match the width. And we'll save it as a JPEG since we don't need to preserve all of the data. And just to compare, let's also try 30% smaller. See how that works. And while we're at it, let's try an extremely small file. It'll be 13% of the original size. We've reloaded Boo. This is the first image we reduced. Its dimensions are matched with the screen. There's no reduction in visual quality. The next image, this one, it was undersized by 30%. You'll notice it's a little blurry, but I find this to be an acceptable level of quality. Then for the last image. For this image, it's 13% of the original size. You'll notice it's extremely blurry with visual artifacts all over. Taking a close look, you'll notice the distortions are lined up 8 pixels by 8 pixels, especially right in here. This was caused by the JPEG file format. Let's look at the file sizes. The original up here is 777,000 bytes. The image that was reduced to match the screen is only 318,000 bytes. That's a 59% reduction in size. The next file, it was reduced, undersized by 30%. It's 157,000 bytes. That's an 80% reduction from the original. For the image quality, that's the one I'll use. The last file, it was reduced to 13% of the original size. It's 23,000 bytes. That's 97% reduction in size, but it's not really usable for our background image. You can always try adjusting the compression ratio for JPEG files, but there will always be a trade-off between image quality and file size. I hope this presentation will help you keep your images small and useful. Since we couldn't possibly cover everything in the video, I encourage you to play around with an image editor and see what works best for your needs.